perfect. Thank you.
Okay, great. So thank everyone. Thanks for the invitation to this conference. I am Giovanni Masciocchi, and I am a PhD student at the University of Mainz. And I did my PhD in collaboration with the company which does magnetoresistive sensors, Sensitec. Today, I would like to present you a method to imprint CMOS compatible strain gradients on a silicon wafer that can be used for spintronic application. And in particular, we will focus our attention today on how this strain can be used on magnetic domain walls. You of course know very well one of the most famous application of domain walls and spintronics, which is the racetrack memory. And this type of application relies on the fact that we can transfer and move the information in a nanowire structure because we can move, for example, by means of electrical currents or external magnetic field, the domain wall that sits between them. Meaning that if we have a field in one direction, we move our domain wall on one side as a quasi-particle, and with the opposite direction of external magnetic field, we move it on the other side. Magnetic domains can be used not only for memory application, but also for sensors. As you can see in this example that I report here, if we have a spiral stripe of magnetic material in a range as a nanowire, the domains that move under the presence of a rotating magnetic field can count the number of rotation performed by an object. And in this domain wall devices, one of the greatest challenge is to control the position of those quasi-particle as they move in the nanowire. And classically, two main approaches has been used. We already saw in the previous presentation the use of notches to control the position of a domain wall using shape anisotropy. And another method employed is a combination of voltage with a piezoelectric substrate to realize a strain in a specific area of the nanowire, which then will pin our domain wall in that point. However, both of these methods, even if widely used, are not appealing for most sensor manufacturing companies, as they would require huge investment either for tools for material deposition or for high resolution lithography machines. In this presentation, I would like to propose you a method to pin a domain wall using strain, but not with the use of piezoelectric substrate in order to target this area of this plot. In order to be able to pin a domain wall using the strain, we need a non-uniform strain in our nanowire. As it is shown by this micromagnetic simulation, a domain wall is trapped by the presence of this strain, as it happens when we play when we play golf and hit the hole on the green. This phenomenon can be explained by the fact that when we have a strain and a magnetostrictive material, the strain itself is causing the presence of a minimum of energy for a domain wall in the strain area, which then has forms a favorable position for the domain wall moving in the racetrack. I told you that we want to use strain to pin our domain wall, but without piezoelectric substrate. So how can we realize such a non-uniform strain? And our idea is to use something that is already present in the fabrication step of most magnetic sensor. It is well known that when we deposit a passivation layer, silicon nitride in our case, on top of a silicon wafer, due to the high temperature of deposition combined with a different thermal expansion coefficient of the two materials, we have a uniform stress induced over the wafer. As you can see from this CMOS simulation, The stress is uniform on the surface and is strong enough to induce a curvature on the wafer itself. Now, this is a uniform stress, and to induce a non-uniform one, that's what we want, we realize some openings in this silicon nitride. You can see in this scanning electron microscopy image what's the result after using etching to have two square openings in the silicon nitride layer. If we look at the strain profile that is now created next to these openings, this is again a finite element simulation, we see that we have a very well localized strain between the two openings. This is exactly what we want, and now I will show you how we can couple this type of strain with a nanowire to see how it influences the dynamics of a domain wall moving in the racetrack. For this, I will consider the following geometry presented in this figure. We have two square openings, creating a compressive strain between them, and then we have a nanowire which passes between them. Now, nanowire, of course, made by magnetostrictive material. To see where the domain wall sits, we use Kerr microscopy images, and as you can see, for very low magnetic field, we have our domain wall placed at the beginning of the nanowire, where the injection path is. If we then increase the magnetic field, applied in the x direction, we move, of course, our domain wall forward, but you see that the domain wall is now trapped in the strain area. This is because of the magnetoelastic coupling and the strain produced by our openings. We need, therefore, a stronger magnetic field to move our domain wall forward to the end of the wire. I've shown you, therefore, that we can use this simple fabrication method to pin a domain wall using a local strain induced. However, can we utilize this type of technology, this type of idea, to realize a device, something which can be useful and not just a demonstration of proof of principle? And for this, we have considered a slightly modified geometry, which again has the magnetostrictive nanowire where the domain wall will move, presented in orange, and always have a pair of openings in the silicon nitride. However, here we have 4 of them, and if you look closely, they are inequivalent, as the distance between them is decreasing, going from left to right. This means, as you can see from the finite element calculation, that the strain and the strain gradient, respectively in blue and orange, will be larger and larger if we move from left to right. Note that here the strain is negative because it's compressive. Let's see what happens to a domain wall moving in this type of device. For low magnetic field, as we expect, we have our domain wall pinned between the first two openings due to the magnetoelastic energy. And now if we increase the field, we can monitor using the Kerr contrast obtained for the image, the position of our domain wall as a function of this external magnetic field, always applied along X. And for larger magnetic fields, we see that we propagate our domain wall from the first pinning site. However, it gets pinned in the second point. That's because here the strain is larger and the pinning force is larger as well. If we now increase our magnetic field further and further and further, we move our domain wall one step forward to the next pinning site until we reach the end of the nanowire. What we have realized here is therefore a magnetic sensor which is able to measure discrete value of external magnetic field. Of course, this is quite interesting, but in an application, we do not want to carry our Kerr microscope on top of our chip and then look with our eyes or with a computer how much the contrast is. So we would like to have electrical readout. And for this, we can consider the same sensor geometry. However, we can realize our magnetic material with a GMR stack. This means that we will have this will allow us to have a readout of the resistance of the strip of the nanowire using this contact configuration here. If we have a domain wall at the beginning of the nanowire for low magnetic field, our free layer and reference layers will be, for example, oriented anti-parallel to each other, and this corresponds to a high resistance level. If we then apply a magnetic field, we move our domain wall forward, and this will change the magnetization of the free layer here, but not on the right. Therefore, we have a lower value of resistance. And obviously, as you might already have guessed, the more we move our domain wall forward, the more we lower the value of resistance, always with in discrete steps. Therefore, we can use this device as a magnetic field sensor able to measure maximum values of external magnetic field or electrical currents if the sensor is placed, for example, next to a Ørsted line. And the great advantage of this solution is that we have no need for external electrical power to operate the sensor. The external power is needed only to read out the information. And now I hope that I convinced you that with this idea we can target the possibility to control domain walls using an inexpensive method. And moreover, this method can be used not only for the specific sensor solution, but by changing the opening geometry, we can realize an arbitrary value of strain and strain gradient. You can see here for a square opening, we have a constant strain, and for a triangular opening, we have a constant gradient of strain. With this, I would like to summarize the content of my presentation, saying that we have realized this type of strain that can be used to pin domain walls in a nanowire, and finally, can be used to realize a new type of magnetic sensor concept. I would like, therefore, to thank the founding agencies and all my collaborators, and I am now happy to answer your question. And in case you have no time, I will be in the coffee break area in Gathertown.
Thank you very much for your nice talk. Are there any questions from the audience? If not, I will ask a quick one. Oh, yeah, there is a question from Diana.
So I think you can hear me.
Yes.
First, thanks, Giovanni, for the presentation. This new concept for sensors is very interesting. I was just wondering, so in this case, you do define a gradient of strain, you can engineer that, but it's only compressive.
Yeah, so you can have the compressive strain if you consider the effective strain along X. So you do the difference between X and Y strain. Then, of course, if you have if you consider the strain along the effective strain along Y, so if you, for example, your nanowire for some reason is along Y, then you will have tensile one. So that it all depends on like the effective strain that you have, so that the difference in the components. But yeah, of course, to change this value, you would have to have a different, let's say, material, a different initial stress on your wafer. Yeah.
Sure, of course. That I understand that. It's interesting that you can just change the direction of the racetrack and then have different types of stress acting on your materials. And just to complement this, the materials on your racetrack, they are paramagnetic and something else.
I was maybe not
strict, no?
Yes. So in this case, we have we are using cobalt iron with composition 70-30. So we have positive magnetostriction around 80 10 to minus 6. We have tried also with cobalt iron boron 40-40-20. We also have positive magnetostriction. It works as well. Of course, the pinning field is a bit lower because magnetostriction is lower. One could use also, we didn't try, but one could also use nickel, has negative magnetostriction, so one has to be careful that there would need a positive strain to get a minimum of energy. Yeah, but yeah, one could use different type of materials, and of course the cool thing is that then you do not need a super high magnetostriction, but the one of cobalt iron boron is enough to see these effects. Yeah.
Thank you.
Welcome.